All right, guys, here we go. In this video, I'm going to go through question number 11 and question number 14, both of which have been requested. So here we go. The number 11 says we got a 300-gram baseball dropped from a height of 2 meters onto a spring with an unknown spring constant. The spring compresses 3.2 centimeters. Find the spring constant. So we've got our baseball, which is 300 grams, hanging out up here. And it's going to fall until it lands on a spring. And then the spring is going to compress 3.2 centimeters. All right, and we know that the height of the drop is 2 meters. So this is going to be conservation of energy as long as we're looking at the ball, earth, spring system. We're going to consider all of those. If there's no air friction, then it's all of those things are part of our system, and it's going to have energy conservation. We'll say the change in energy is equal to the change in kinetic plus the change in gravitational potential plus the change in elastic potential. Now, it's starting at rest, and when the ball lands on the spring's going to compress, and at some point the spring's going to stop. That's when it's compressed 3.2 centimeters, and then, yeah, it could launch the ball back in the other direction. But the question is, if the spring compresses this far, that's the maximum compression there of the spring. At that point, the object will be at rest. And so it starts at rest, it ends at rest, and so there will be no change in kinetic energy. It doesn't matter that it's changing in between. All that matters is the beginning point and the ending point. So, and we know that energy is being conserved. There are no outside forces other than gravity and the spring, which are both accounted for here. So we can go ahead and rewrite this equation. It's now going to be 0 equals the change in gravitational potential energy, mgh final, minus mgh initial. And then we're going to add on the change in the elastic potential energy. That's 1/2 kx squared final minus 1/2 kx squared initial. Again, if we dig in a little bit deeper, we notice that when we get down to the ground, that it's going to be basically on the ground. So this, sorry, not that one. The final height is going to be 0, so that's going to take that away. And then initially, the spring isn't compressed. And so initially, this isn't going to matter either. There's going to be no elastic potential energy in the beginning because the ball and the spring aren't interacting yet. And so finally, we're down to this, where we can go ahead and put in the numbers. Negative mass, which is 300 grams, that's 0.3 kilograms, times g, which I'll put in as 10, times the initial height, which was 2 meters high. And then we'll go plus 1/2 times k, that's what we're looking for, times x, which is the compression. So that's going to be 0.032 squared because it's given to me in centimeters, and as we know, it should always be in meters. At this point, I've got an equation, and I should be able to solve for k. So go ahead and do that, and you should get, you should get 11718.75. So k equals, I got 11718.75. Now you'll notice that I guess most of these are one significant figure, but in class we said, you know what, just write 3, so it's okay if we just round it then to 11700, and it's newtons per meter is for k. All right. There you go. There's your spring constant. That's number 11. Notice again that the kinetic energy in the middle is not important. This is not a huge multi-step question. As long as energy is conserved for the whole situation, the only forces here are the gravitational force and the elastic force when the spring hits it. Those are the only two forces. Therefore, energy is conserved throughout. And so we don't have to worry about the middle stages. All that matters is the beginning and the end. This is very similar to what we talked about before when somebody throws a ball up or down. It's the same thing, and we're actually going to see that right now. Okay, so question number 14. Waleed throws a 10-gram ball straight down from a height of 2 meters. The ball strikes the floor with a speed of 7.5 meters per second. Assume no air resistance. Show your work and use energy conservation. What was the initial speed of the ball? Okay, so they want us to use energy conservation. So we know right off we're going to be using change in E equals the change in kinetic energy plus the change in gravitational potential plus the change in elastic potential. No springs this time, so that guy's going out. It does say that there is no air resistance, which means that gravity is the only force. So the total change in energy should be 0. So that leads us to 0 equals the change in kinetic energy. So that's 1/2 mv final squared minus 1/2 mv initial squared. And then we're going to add on the change in gravitational potential energy, which is mgh final minus mgh initial. And so we should be able to put some of these numbers in. We do know actually that the final height is 0, so that guy's going to go away. But otherwise, we can put numbers in. Sometimes the kinetic energy goes away, but it does say that it strikes the floor with the speed of 7.5, and it does say that he throws the ball straight down. And so that's going to give us a different answer here. So numbers 1/2, we got the mass, which is 0.010, times the final velocity. It says it strikes the floor with the speed of 7.5, so that's going to be 7.5 squared minus 1/2. Again, the mass was 0.010 times the initial velocity, and that's the question, right? What was the initial speed? So we'll leave that there. Minus, and then we've got the mass again, 0.010 mass times gravity, which will go 10, and then times the initial height there, which was 2 meters. All right, so again, all we have left is the V here. So you should be able to find out each of these numbers and solve. So the first thing I'm going to do is I'll go ahead and simplify a little bit. I know some people, this is a little bit daunting, the algebra here, so I'm just going to go ahead and simplify a little bit first. So 0 equals 0.28125, and then minus, that'll be 0.005 V naught squared. And then over here, that's 0.010 times 10 times 2, which is 0.2, like that. And so then I can move these two guys over to the other side. So I'll subtract the 0.28 and then add the 0.2. And we should get a negative 0.08 equals negative 0.005 V naught squared. And so we divide by that 0.005, and then we square root it, and we get an initial velocity of 4 meters per second. All right, so we got our speed there. That's the initial speed going down, is 4 meters per second. And now the question is, if he now throws the ball straight up with the same speed, with what strike will it hit the ground? And the answer is, well, it's going to hit the ground with a speed, of 7.5 meters per second. And the reason why, of course, is conservation of energy, right? It's starting with all the same information. It's still going to be thrown up with the speed of 4 meters per second. So its initial kinetic energy is the same. It doesn't matter if the kinetic energy is up or down because it's a scalar. It's not a vector. Direction doesn't matter. It has the same initial gravitational potential energy, right? All of the things that you see in the equation are the same. The final kinetic energy will end up being the same. Why? Because the initial kinetic energy is the same and the initial gravitational potential energy is the same. If these two guys right here don't change and the mass doesn't change, then the final speed can't change either in order for it to be equal. And so therefore, because of conservation of energy, it doesn't matter if he throws the ball straight up or straight down, or even if he throws it out at an angle, it should give him exactly the same speed every time. All right, and that's it. Go ahead. Hopefully that was helpful for you, and I'll see you soon.